It's my pleasure to introduce our speaker for this afternoon's talk, who is coming at the biofuel story from the synthetic heterogeneous catalysis perspective, Professor Wolfgang Holderich, who comes to us from Aachen University in Germany. Just a brief summary of Professor Holderich's rich career. He began his studies in chemistry at the University of Karlsruhe in Germany. Chemical engineering and chemistry are more integrated, I would say, in the European system than they are as separate undergraduate degrees here in the US. He continued his studies at Karlsruhe, where he finished his PhD in 1975 with Professor Gerhard Fritz, and then did a 2-year postdoc stint at MIT with Professor Seyferth, Dietmar Seyferth, and then did 15 years where he grew into the position of head of catalysis at BASF AG, and was on the corporate board for directions in catalysis at BASF, which is considered to be, I think now, the world's largest chemical company. After this, in 1992, he accepted his position at the university where he is now, and where he's the director of the Chemical Technology and Heterogeneous Catalysis program. Professor Holderich's expertise is really amazing. I remember first meeting him actually as a graduate student at Caltech.
Long time ago.
Having beers with him at the equivalent of our Bear's Lair after the seminar, and hopefully some of you will have a chance to meet him after the seminar. I was amazed at how approachable he is and how friendly he is and down to earth he is for a person of such distinguished stature, even back then, and that was a while ago. And then, so feel free to ask questions. And also I'd like to note that this seminar is brought to you by your colleague, Al Charmeau, as part of the EBI seminar initiative of students and postdocs at EBI inviting speakers. So this is made possible by you, so thank you for that. Professor Holderich's career spans many awards, starting from Outstanding Thesis Award during his PhD dissertation, then an NSF NATO postdoctoral fellowship, and recently he was awarded the Murphree ACS Award for excellence in industrial and applied chemistry. His research spans everything from fine chemicals to intermediate chemicals, and today he'll tell us about biofuels. So thank you for coming, and it's a pleasure to have you here.
Yeah, thank you very much, Alex, for your kind introduction. I didn't remember that we met such a long time ago at Caltech. Anyway, it's a pleasure to be here, and thank you very much for showing up to listen to me. And today I will give you a flavor of what we are doing, certainly in our group. Certainly that's not the only project we have and not the only field we are working in. We are pretty broad, but I will give you nevertheless a few aspects of our work in the use of renewable feedstock as a contribution for environmental protection. So when I say environmental protection, that is more or less the headline for our institute. We use heterogeneous catalysis to do environmental protection. And I hope that it will come through today when I give this talk. So when we look around in our world, then we realize some most pressing environmental issues. And all of you are aware of the global climate change. We hear about the food production problems. We hear, of course, that our non-renewable resources are diminishing, depleting. Then we have still a lot of toxic materials we use in our chemistry, in our daily life. And the most pressing issue, and I will not touch that today, but that is the most pressing issue, is a sustainable energy production. And I spoke to my wife about 1 hour ago on phone, and she said, oh, there was an interesting article in the German newspaper telling us that we consume more crude oil than we find. Yes, in the former days we found more than we consumed, but now we are already on the decline. Yeah? So we have to find also something else here. Yeah, and how can we help from the side of chemistry in that field? We speak about green chemistry. Not in Germany, we speak about environmentally friendly and sustainable chemistry, but normally we do not use this term green because we have a very I don't want to say efficient party, but we have a party which is called green, and so we don't want to go in the same direction with them in some cases, and you will see during my talk what I'm speaking about. Anyway, when we do that, then we can look, for example, for alternative reagents. We also can look for alternative solvents or alternative products. And we also can use alternative feedstocks in contrast to use mineral oil, and that can be combined by the use of alternative catalysts. And that will be my topic of my talk today. Already in 1992, politicians and representatives of the chemical industry and also of the academia, they came together in Rio de Janeiro. At that time, in 1992, they committed that the sustainable use of renewable natural resources is important. And that is one of the aims in this Agenda 21 of Rio de Janeiro for our century. And since that time, the picture changed quite a bit. And where do we find such alternative feedstocks? We find it in waste biomass, you are aware of that, forestry residues, industrial waste from the food industry. Then you are working here in the field of cellulose and to convert cellulose to certain other compounds. Then we have crops we grow. Mara just showed us what we can use, straw, yeah. And then we also can plant crops, specialty crops. Now, when we look around where we do find all these crops, for example, where is the global biomass availability? The crops contribute with 1.7 billion metric tons per year to the biomass we can use. And surprisingly, I didn't expect that, most of that we get from Asia, about 1 billion metric tons, followed by the Americans, that means the whole continent, and then the Europeans and the Africans later on. But why in Asia so much? Our Asian friends, they eat too much rice. So the rice straw contributes tremendously to that number. It's almost 1/3, 40%. Yeah? So that is certainly a source we should consider. And the Japanese and others consider that very much in Asia. However, when we do such kind of chemistry and we want to use a renewable feedstock, then we have to look always in comparison with our situation in petrochemistry. We have always to make a comparison. For that, we have to see the strengths and the weaknesses of petrochemistry. We have to see the strengths and the weaknesses of the use of alternative feedstocks. When we look at the strengths of petrochemistry, then we have to say we have a known technology. We developed that technology over the last 120, 150 years. Well known. Furthermore, we spend a lot of money, we invested a lot of money over these years in plants. We have existing plants. And I have been in Singapore, and there is a new plant now of ExxonMobil for a steam cracker. for 100,000 tons of ethylene for $4 billion US. That's an investment, and you have to consider that. Furthermore, the chemistry of the materials or of the compounds in petrochemistry are quite easy. We have normally to deal with paraffins. But there is already one of the weaknesses, because we have to functionalize these compounds. We want to have aldehydes, we want to have ketones, we want to have carboxylic groups, we want to have amines, and so on. So we have to make out of that functional compounds. Furthermore, we have another weakness, and that is the pollution. Everybody knows that crude oil and natural gas contain sulfur, and we do desulfurization and so on. And the depleting of the resources. These are the weaknesses. Now we look at the alternative feedstocks. There is only low environmental impact. We have a lot of functional groups in our starting materials. That means in a sugar molecule we have about 6 hydroxyl groups, and each of that can react. These compounds are not toxic. They are biodegradable, and of course we can grow that in Illinois, as you do it, yeah, or in our neighborhood. But now we want to see the weaknesses. These are advantages, certainly, but the weaknesses is the chemistry is quite complex. As I told you, we have a lot of functional groups in a molecule. But what we want to do is we want to have highly selective reactions, and that will be difficult. Then the technology is unknown. We have to create new technology from the scratch. And this new technology has to be evaluated. And these two factors have to be compared with the strengths of petrochemistry. So when we develop new technologies, that means a lot of efforts in research and development and a lot of efforts in making new investments. And that has to be compared with already paid off existing plants. And you will see that it's not so easy. And I will touch that during the talk too. So it's not a new field when we think of biomass. It's quite an old field. Everybody knows about the cellulose and pulp from the wood. Yeah, we produce about 10 million tons a year. Then we know about fibers from cotton, about 15 million tons a year. We make a lot of chemicals, surfactants, detergents, lubricants from fats and oils, also about 10 million tons a year. And I don't want to mention wine and beer by fermentation. Yeah? You are aware of that. But recently, we follow a new trend. And this new trend means we should look, can we use such renewable feedstock for the production of value-added chemicals? Or can we modify this renewable feedstock in a way that we get new materials with new properties, favorable properties, such as surface activity or biodegradability? And furthermore, we also can consider, can we make already existing compounds which we use in our chemistry, can we make these in a cheaper and ecologically safer way than before, or as we do it currently. So that's certainly a field of sustainability and green chemistry. Just to give you a few figures, in Germany, and that is true for the United States, and you will know that even better than I do, about 10% of all the materials we produced are based on renewable feedstocks. The National Research Council in the US estimated that this number will be increased to 25% by the year 2020. And I spoke to a female. I don't have anything against females, but she was a female from the Green Party in Germany. And she said to me, by 2020, they want to see 40% of all the chemicals we produce in Germany should be based on renewable feedstock. That is ridiculous. cannot be managed, not at all. Yeah, and even so, they have that on their program, but that is not possible. Anyway, in Germany we use about 50% based on fats and oils, 43% based on carbohydrates, and the rest based on proteins and so on. But it's not only an ecological effect in Germany, we have also an economic effect. We produce about 20 million tons of organic raw materials, or that's the consumption, the annual consumption in Germany, based on crude oil with 75% and natural gas with about 75%, followed by coal. That was surprising for me, still 15%, and 10%, I spoke about that already, the renewable feedstock. However, these 10% make 22% of the profit in the chemical industry. So that means we produce a lot of chemicals, value-added chemicals, out of renewable feedstock. And that must be an incentive for us. Yeah? Okay, now let's go to my first statement. And I say, the nature is the architect of the carbon framework. What does it mean? Right now, we do chemistry in a way that we cleave first all the long chain hydrocarbons in a steam cracker down to ethylene, propylene, butene, and aromatics. And then we start to build up the molecules to synthesize the molecules we need. We use benzene and ethylene, make ethyl benzene, out of that dehydrogenation, styrene, and so on. But we also can think, can we find such carbon frameworks we need? Can we find such carbon frameworks already in our nature? Yeah? Can we start on a higher synthesis level? And there are some examples we studied in our group. That is camphoranic aldehyde from pinene epoxide, parathymine from limonene, mangrove root arome from limonene and pinene, grapefruit arome, limonene, pinene, acrolein, acrylic acid from glycerol, and so on. So there are some examples. I want to make that clear on this example. That is parathymine, yeah? That is a methyl group, and here you have an isopropyl group. And this parathymine is a very good solvent. It's also used in perfumes as ingredient, as a blend. And sometimes ladies complain about the perfume when they put it on the skin and it starts burning. And then you use the cheap perfume because the blend is isopropanol and that evaporizes. Yeah? However, if you use a more expensive blend, parathymine, you do not have that effect. Yeah? So that is, immediately I can tell you if it's a cheap or not so cheap perfume. But the major purpose of that parathymine is the production of paragrisol. You have this isopropyl group, and by Hoch synthesis you can convert that in acetone and a hydroxy group. So you get a paragrisol. And the paragrisol is then alkylated with isobutene to 2,6-D-tertiabutyl paragrisol. And that is the most common and most used antioxidant we have. It's in each sun lotion, in each sun cream. And you certainly have seen certain numbers on the sun lotion, 12 or 20 or even higher. Yeah? When you go to the Antarctica, then you need a factor of more than 50. And that is a concentration of this 2,6-D-tertiabutyl paragrisol. Anyway, the synthesis based on the petrochemical feedstock starts with toluene, propylene, and you get the 3 isomers. And these isomers has to be separated. That can be done by UOP process, Cymex process, or it can be done by partial crystallization as it was developed by Sumitomo Chemicals. But now we look into nature. Here, it's the same framework. And that is limonene. You find limonene in each citrus fruit, lemon or orange, you find that. The only thing what you have to do is to shift the double bond from the isopropylene group to the ring system and to make a dehydrogenation. Then you have the same compound you need. But the advantage is that we do not need any separation anymore from the ortho and para, ortho and meta. You have already the para structure you need. That can be done by the use of a palladium silica catalyst, and we have done in the gas phase, and we have done that. Oh, something is wrong now.
Put it in your pocket.
Maybe it's better to put it in the pocket, because my belly is too huge for that. Okay, we have done that in the gas phase in a fixed bed reactor, and we obtained 98% yield over a long time, service time of more than 800 hours, and when we run the reaction. And also what I mentioned just briefly is, depending on the silica source for your palladium, you have a good catalyst or a bad catalyst. So only in one case here, you can see we get the 98, 99% yield. Limonene, you get always a side product during the orange juice production or lemon juice production and so on, was for us still too expensive. So we looked around, can we find cheaper materials? And we found that Arizona Chemicals in Wilmington, Delaware, they produce a so-called dipentene. And that is a mixture of alpha-limonene, camphene, cineol, pinenes, other turpentines, and also some parathymine. Also that mixture, and to make this story very short, can be converted completely to the parathymine. Now the cheapest source we have for turpentines are the so-called crude sulfate turpentine. That is the cheapest and the major source, and we get that by the pulp digestion in a graph paper mill when we produce paper and pulp. And now we make a calculation. You get that material for about 50 cents per kilogram. These are old figures, yeah, when you see this 40 cents. And we compare now this that amount of money we have to spend per kilogram with the starting materials based on the petrochemistry. 26% for toluene and 44% for propylene. Now it's, I think, 1,200 per ton, so it's $1.20, yeah? When you compare that now, then you see we have a much cheaper feedstock, 4 times, 5 times, or even more cheaper feedstock to produce the same compound. That was now developed then with the Latuku craft paper mill in Latuku, Canada. They have in the effluent, in the wastewater, a lot of pinene, and we can convert that to the parathymine. So we had quite a good developed a quite good technology. We look now around a little bit, and what else can we do with pinene and limonene? And here we have this pinene epoxide. That pinene epoxide can be converted to camphoranic aldehyde. That reaction is done in a larger scale and in the presence of zinc bromide or zinc chloride. And you know, when you use such Lewis acids, then you have to neutralize later on. You create HCl, you create HBr. But the worst part here was you create also soluble zinc compounds. And these zinc compounds have been in the wasted water. And the wasted water was brought to the sludge treatment. And the bacteria in the sludge treatment do not like copper or zinc or similar transition metals. So the sludge treatment broke down, let's say, every 4 weeks. Therefore, there was a big need to develop a heterogeneous catalyst. We managed that, and we used later on ultra-stable Y-zeolite in the liquid phase at lower temperatures of about 0 degrees, but then we were successful to obtain that compound with about 85% yield. Why is that compound so interesting? Out of that compound, out of that camphoranic aldehyde, you can make in aldol condensation different compounds as shown here. And these are sandalwood fragrances, synthesized sandalwood fragrances, which have the same smell as a natural occurring sandalwood oil. And one of these compounds is a major component, is a fragrance in one of the most famous perfumes. And you should find out now which it is. Mara, I told you, you will be the one who has the first choice to find out that.
This is not my area of expertise.
My wife will be suspicious.
But I tell you, that is a perfume not only for women, it was the first perfume for men and women. Lady, okay. You do not know. Okay. What do you think, Mara?
Not my area of expertise, unfortunately.
Yeah, I can imagine.
CK1.
Correct. That's CK1. That is CK1. Kelvin got very rich with that. And the company we developed it, for which we developed that, made also a lot of profit. But I'm still here and not on the beach in Hawaii. Yeah, so you know how much I might. Yeah. Anyway, so that is one example. If it, I cannot tell you that. Then we have this limonene or pinene structure here again. And now we add to the isopropylene group, we add H2S. And then you get this thioether. And that is a grapefruit aroma. Yeah? Smells badly. But the whole production of the year, 300 kilogram, it's in the Lake of Geneva, Lac Le Mans, is sufficient to have a big grapefruit bottle, which is very good. Yeah. Anyway, I don't want to speak more about that. Then we have here also the limonene structure again, yeah. And the only thing is you added an alcohol to the isopropylene group and you made a hydroformylation at that double bond. So you get a lot of compounds. One of those is mango aroma. These compounds are depending, or the smell of the compounds are depending on the alcohol you add. Yeah. So we get, in the case of methanol, the mango fruit aroma. In the case of ethanol, the green citrus fragrance. You know, you like to drink Corona with a lemon. Yeah. That's here. And then we have fresh grass flavor, we have woody odor, and so on. We can make quite a number of different compounds out of that. Now let's change the topic. Now we come to the field of biodiesel, which is more maybe familiar to you. And I want to show you now what we are doing in that field, or at least part of it. You know, the first generation of biodiesel started with triglyceride, transesterification with methanol to form biodiesel, diglyceride, again transesterification, monoglyceride and biodiesel. And the last step, we get glycerol and biodiesel. We carry out this reaction in the presence of sodium hydroxide or sodium alcoholates, and we are quite efficient. But not so efficient. Here we have the example in the homogeneous case when we make this basic transesterification. You see the triglyceride is going down, the biodiesel is going up, also the glycerol is going up, and between we have mono and diglyceride as an intermediate. But what you can see out of that picture is that we cannot achieve 100% yield. And therefore, in an industrial plant, you have to use two-step procedure. That's a Berkeley process as developed in Germany. But also what I want to point out here, after the reaction, you have to neutralize your sodium hydroxide and your sodium alcoholate, so you add HCl. And that causes some problems. Now, the disadvantages of this conventional biodiesel process is, even so we have very high efficiency with respect to the basic catalyst, sodium hydroxide, afterwards we have to neutralize. Then we have salt formation. And our crude glycerol, which we obtain, contains these salts. So when we want to use glycerol for further synthesis as a chemical platform molecule, then we need purification by distillation, which costs money. Furthermore, these triglycerides we use in the biodiesel production of the first generation has to be clean. That means we should have no high fatty acid content in that. We have to refine it before we use it. Yeah, so we cannot use low quality fats and quality oils with high free fatty acids. It's a problem. Therefore, there was a need to simplify this technology, and we wanted to use the heterogeneous catalysis as a powerful tool. And we have chosen as heterogeneous catalysts rare earth oxides. And we checked that in autoclaves and continuous flow fixed bed reactor. Here that's a preparation briefly how we make these rare earth oxides. We start from the nitrate, add oxalic acids, and you precipitate the lanthanum oxalates, and afterwards it's calcine. But you have to calcine it higher than 850 degrees. Otherwise you have carbonates as phases which disturb the reactions. You get excellent, nicely crystalline materials, fantastic, and you get unfortunately only 5 square meters per gram in the BT surface. I don't want to go in detail, but we use these materials now for different oils, for different fats and oils. So we used rapeseed oil, refined palm oil, crude palm oil, and brown grease from pork. And the difference between these 4 materials I have chosen for that lecture are that we have different content on free fatty acid. In the case of rapeseed oil, no free fatty acids, therefore rapeseed oil was always used as starting material for the biodiesel of the first generation. Then refined palm oil, also no free fatty acid. However, crude palm oil, 5% free fatty acid. And if you use brown grease from pork, 12% free fatty acid. That cannot be used in a unit of the first generation, yes, and with using sodium hydroxide or sodium alcoholate. We use that, and that is a unit now of autoclaves we have. Here are some results. We use a refined palm oil. And in the blank test, we have a little bit of the desired biodiesel, but mainly the triglyceride. And however, when we add now the lanthanum oxide at low temperatures, yeah, then you see we get a lot of biodiesel, a little bit monoglyceride, diglyceride, and some leftover of triglyceride. Now we do the same experiments in the case of crude palm oil, which contains 5% of free fatty acid. And surprisingly, you see the results have been even better. No triglyceride, no diglyceride, almost all biodiesel. And also in the blank test, we had more of the biodiesel already. What was the reason? The reason was that the crude palm oil, which contains free fatty acid, solve the part of the lanthanum oxide, and then you do not have a heterogeneous catalyst. It's leaching, it's going in solution, and you have homogeneous catalysis. And that's not what we want to have. So the disadvantage is that we can say, of course, we have rare earth metals which give nice catalysis. However, they react with a free fatty acid to make a soap, and then we have leaching. That's not what we need, because then we have a poor long-term stability, and that is certainly not for an industrial process. That means we have to avoid the soap formation. And how can we do that? We have done that by immobilization of these rare earth metal oxides on different support. And one of the most efficient supports was tetragonal zirconia. That was a very good support. I don't want to explain now the different preparation steps, but one of the advantages was we have now a much larger BT surface, not 5 square meters per gram, we have 55. And also we have large pores with 8 nanometers, so we do not have any diffusion problems. If you use now such a material, 20% of lanthanum oxide on tetragonal zirconia, then you get nicely in the batch reactor the biodiesel in addition with some monoglyceride and diglyceride and triglyceride. But it was working nicely. We have done that at 200 degrees. Fine. After that, we dared to go in a fixed bed reactor. For that, we made extrudates. We have a fixed bed reactor with 2 centimeter in diameter, 36 centimeter in length, so we could fill in about 125 cubic centimeter catalyst volume. That is a unit. Here you have the methanol and the oil on 2 balances. The pumps, this mixture is pumped through the catalyst bed. Here you have a pressure regulation, pressure control, and then the pressure release and the condensation. And the product is again on a balance. That means we can exactly find the C balance of that process, and the C balance was 99%. We have no loss, not at all. Okay, that is the unit, the 2 pumps. Then it's going in the reactor here. Then this is a pressure control. Here we have the condensation. That is a biodiesel, methanol, and glycerol. Okay. Now a few experiments. We have to shift the equilibrium. Therefore, we use now a lot of methanol in this fixed bed reactor, 50% of methanol, and you see we come up to 98, 96, 97, 98% yield of our biodiesel. And the yield of our glycerol is quite similar, also above 96%. We also can change the temperature. We change the temperature between 175 and 225, and you see the biodiesel production is about 98% yield, and the glycerol is about 96% yield. But what I want to say here is we do not need 2 reactors anymore. We can manage everything in one single reactor to obtain 100% yield. Okay, now the interesting part. We have this lanthanum, 20% on zirconia. I showed you examples with rapeseed oil. Now we use a brown grease of pork, which contains 12% of free fatty acid. And we look here for the biodiesel. You see, increase up to 98, 99%. Our triglyceride is going down below 0.5%. Our monoglyceride is also going down below 1.5%. Our diglyceride is going down below 1%. But the most interesting part is now that our free fatty acid is going down from 12% down to less than 1%. What happened? In the case of the transesterification, we need basic sites. But for the esterification, which takes place here, the free fatty acid with the methanol to form the biodiesel, these acid sites. Okay, so we have that interesting result. And also it was interesting to get 98% pure glycerol. The reason is shown here. We have not a basic catalyst. We have not an acid catalyst. We have both. We have, according to the CO desorption TPD, we have weak basic sites and strong basic sites. We have weak acid sites according to the ammonia TPD and strong acid sites. Weak acid sites, strong. So we have a bifunctional catalyst with basic sites and acid sites to make the transesterification and the esterification simultaneously, and that enables us to use now each fat, each oil, doesn't matter how much free fatty acid is in it. Yeah? Okay. So we said material, lanthanum and zirconia, we have a very active and stable heterogeneous catalyst. We do not have leaching. Why? Because the lanthanum oxide is incorporated in the tetragonal voids of the zirconia and doesn't come off. There is a binding between. Yeah? And so we can use that for free fatty acid containing materials. We get now a glycerol which is free of any salts in a very high purity. And that enables us now to become glycerol as a platform molecule for the production of different chemicals like acrolein, acrylic acid, allylic alcohol, 1,3-propandiol. And after that, I will go over to use now glycerol. And here, you are aware that glycerol is used in cosmetics, lubricants, explosives, pharmaceuticals, and more than 1,500 different applications. And my cousin in LA, he told me he was on the way from Las Vegas to LA, and finally they stopped him because there was an interesting analysis on the way, on the highway or on the street. And they stopped him, a lot of police around him. What happened? Since he asked him, do you have any explosives with you? He said, no. Please open the trunk, and so on. Finally, it turned out, before he left Las Vegas, he used some Avon. You know this perfume, Avon, or how do you say Avon? In French, we say Avon, yeah, Avon. And that contains glycerol. And they detected this glycerol with their machine. So it's very good analysis, but they looked for nitroglycerol, yeah, and such things, yeah. But that was a nice story. Anyway, so you have a lot of applications, but when we produce now biodiesel, we do not speak about 1 ton. Yeah, we speak about thousands of tons. And because we get per ton of biodiesel, we get 100 kilogram of glycerol. That means by the year 2015 in Germany, Europe, we get 1 million ton of glycerol. And this amount cannot be taken anymore by these applications. You have to find other applications. And together with the French company Arkema, we looked for such other applications. And here there are different methods what you can use or which you can apply for the production of chemicals out of glycerol. We concentrated on acrolein and acrylic acid together with Arkema, because Arkema is is the third largest acrylic acid producer of the world, starting with BASF and Roman Haas. And so they had interest here. Yeah, and when you have acrolein, it's a very important intermediate for different compounds. And out of that, you can also make the superabsorbers and acrylates as dyes. But major application is here for diapers as superabsorber. And that is now replaced by not anymore using propylene as starting material, using now glycerol. So we substitute the propylene by glycerol for the acrolein production. And so we also make a further step in the crude oil independency. And the biodiesel producers are quite happy about that, because that gives them now a chance to use the glycerol for a good application, to encourage them to produce more of this biodiesel, and not to think, what should I do with the glycerol? Because in the United States, they fed that to the animals or they burned it. And that is not a good idea, because you have a C3 unit. And when you have a C3 unit, you should consider what you can make out of it. In particular, when you see that the propylene price is going up and the glycerol price is going down. So these are units. Now, I mentioned to you already, when you have glycerol and when you have a renewable feedstock, you have a lot of functional groups. And these functional groups can make reactions, different reactions. So glycerol, for example, can oligomerize, can dehydrate to hydroxypropanone. Out of glycerol and the product, acrolein, you can make acetalization. Also, you can hydrate the acrolein to hydroxypropanol. Out of that, you can make 1,3-propandiol. So you can get quite a number of different compounds. But what we want to have is only acrolein and not all the other compounds. In particular, we do not want to have HPO, because HPO cannot be separated from acrolein and acrylic acid, and it disturbs later on the polymerization of acrylic acid to the acrylates. So we have to get rid of that. Now we made, for example, one experiment at 280 degrees in a fixed bed reactor, and we used glycerol, and you see we had fast deactivation using a beta zeolite. Here it's going down. The yield was about 60%, but unfortunately we had also a lot of these HPO. That is a light blue cross here on top with more than 10%. And just by chance, we found, when we add now oxygen to the system, no deactivation. Same yield or even better, and no, and that is important, no HPO. Don't ask me why. We do not know that exactly. We have an idea, but we do not know exactly. But all the time when we use now in our catalyst screening oxygen, yeah, then we found that the byproduct formation was reduced. And finally, we found a catalyst that was tungsten on zirconia. Without oxygen, we found 100% conversion and 70% of acrolein, and that means a yield of acrolein of 70%. Now we add to the system oxygen, as shown here, and we carried out experiments at different temperatures. You have here the conversion and the selectivity versus the temperature. And so you can see around 280, 300 degrees, I think that was the wrong direction. So you have a maximum, 100% conversion and more than 80% of the selectivity and 80% yield of acrolein. I skip that. Tungsten on zirconia is an expensive catalyst. Zirconia is expensive. Therefore, we looked for cheaper carrier material, tungsten on titania. And with that, we could also achieve nice results. But for that, it was very, very much important that we had found the right titania source. And there was only one source we found from the Sachtleben company, Hornbeck 2, which gave us similar results as with zirconia. Okay, that is our model tube, 1 meter 20 and a diameter of about 1 inch. And we carried out this reaction in that model tube. In the meantime, there's even a larger unit. Yeah? Okay, out of acrolein you can make, in a further reaction step in oxidation, in a tandem reactor you can make the acrylic acid. And here is shown such a tandem unit. We feed in here additional oxygen between them. First reactor, acrolein, second reactor, acrylic acid. So by the end, we can say we have very good catalyst, tungsten on zirconia, tungsten on titania. But in the case of the zirconia, we have to be aware that we have an expensive catalyst. And furthermore, when you have basic sites in that catalytic system, then you get a lot of this hydroxypropanone, and that has to be avoided. Therefore, you have to calcine at very high temperatures this catalyst, and then you destroy the basic sites, and then you get good catalytic activity and no formation of hydroxypropanone anymore. That can be avoided by using this tungsten titania catalyst. And also it was interesting to find that the presence of oxygen suppresses your byproducts and also inhibits the catalyst deactivation. But for that, it is very important, you have an acid catalyst, it's very important that you have alkali-free glycerol. You cannot make with a glycerol out of the normal units using sodium hydroxide or sodium alcoholate. You cannot use that. You must have alkali-free glycerol. Anyway, the best results we obtain now in an even larger unit, it's 85% selectivity and at 100% conversion of glycerol. Okay. Now, Alex, you told me we start normally 15 minutes later because people come late. But you also promised me you give me 15 minutes more.
For you, Wolfgang.
Yes. Yeah. Okay, thank you. But we are speaking about environmental protection. And I will focus a little bit here on the environmentally benign lubricants. And what is the reason for that? If you look around in Germany, we have a consumption of lubricants of 1.2 million tons a year. But we have a loss of 0.5 million tons, about half of it. And we lose that by spillage, by accidents. Also, the students make the oil exchange by themselves. And then they do not consider so much, at least when I have done it, what to do with the old oil. Yeah? And so you have big loss. But the major loss is by evaporation. Think of the car. In the engines, you have high temperatures. Think of the body press to make the body of a car. You have very high temperatures and high pressures. So you lose a lot of these lubricants in form of gases anywhere in our environment. And why is that so dangerous? That's environmental pollution, of course. But dangerous is it? Because we always add to our lubricants based on mineral oil, we add additives. You know that. Molybdenum sulfide, polysulfides, phosphates, and so on. These are toxic compounds. But we need these additives, otherwise we wouldn't get the right properties of our lubricants. These are hardly biodegrade or not biodegrade, hazardous and toxic, and they cannot be recycled. Big problem. So we had a project from the German government. And we looked at renewable feedstocks, and we said, okay, we have double bonds. We have this CH group, which is active. We have ester groups. What can we do? So one of the solutions was that we epoxidized the double bond to get the oxyrane. And then we added to the oxyrane different nucleophiles, for example, an alcohol here. And you obtain then cis hydroxy ethers. Cis hydroxy ethers. Now, first, let's focus a little bit on this epoxidation of oleoesters. And we used first the titania MCM41. You see here is a yield of the epoxide versus the time, and you see depending on the titania content, you have an increase. Selectivity is always better than 95%. Very good. I don't want to go in detail here, but for us, the titania MCM41 is a too expensive catalyst. And when you want to make lubricants, you don't want to make only 100 grams, you want to make tons. And therefore, we considered a cheaper catalyst. And so we looked for a cheaper silica source and cheaper titania source, made a salt gel procedure, and found a titania silica catalyst. And we used that titania silica catalyst also for our reaction. And we could also see we get nicely the epoxidation, also with selectivities higher than 95%. Okay, the only difference was that we did not achieve the same yield as in the case of titania MCM41. When I come back to that, you see we had about 60% after 24 hours, and now we have about 40%. What was the reason? The reason is MCM41 has a huge PET surface, about 1,200 square meters per gram. The silica, which we could make, had only about 700. But what we have done then, we related our activity to 1 square meter of PET surface. And then you see the activity for the titania MCM41 and the titania silica with the same content of titania is the same. No change. The only problem is, of course, when we use the titania silica, which is a much, much, much cheaper catalyst, we have to increase the volume of our reactor, because to achieve the same space-time yield. But that makes more sense than to use titania MCM41. Okay, the catalyst does not leach, that's a hot filtration test, and it can be recycled also, no problem. Now we add to this epoxide, we add now an alcohol. You have the hydroxy ether, fine. And that can be catalyzed just by smectite. You get nice conversion in short time in this epoxidation. So we could add different alcohols. And that is what we have done. We added different alcohols to the system, and we got different lubricants depending on the alcohol. And each of that lubricant had another property. And here is shown the kinetic viscosity of the different lubricants. And what we have done now, afterwards, that means not we have done it, firma Fuchs Petrolub, which is also in the United States. It's a company in Mannheim in Germany. They have used these different lubricants, mixed it in a certain way, in such a way that they got exactly, by that mixing, exactly the properties they needed. But they do not use any additives anymore. So you have really a biodegradable lubricant, not toxic. And that is applied in the forest. When you have these chainsaws to cut the trees, you have always to give oil on that. and you have always a spill of oil, spillage, and that goes into groundwater. And that can be, in this case, biodegradable within a few months. No problem. If you have a truck to pull out the stems out of the forest, you have to use that. But you would say, why don't we use it now everywhere? The problem, surprise. This technology is 5-6 times more expensive than the mineral oil-based lubricants. So we face a problem that we have excellent materials, but they are much more expensive than our materials based on mineral oil. In other words, our mineral oil, our crude oil is still too cheap to be competitive. Anyway, we have scaled up that, as you can see here, first from a 50 milliliter reactor to 2-liter reactors and 4 or 5-liter reactor, and afterwards in our pilot plant in Aachen, we have here a 30-liter reactor. These are the storage vessels, and we can produce these oils in that. And you see here's a big vessel, the stirrer, the condensation of the alcohol, and so on. That was nicely done, and it worked, and it's commercialized in the meantime. And we have some applications, but only in niches. We cannot use it for cars on our streets. It's too expensive. Anyway, so that can be summarized that we can say this titania silica catalyst is as good as the titania MCM41, but it's much, much cheaper. Also, we can say the addition of nucleophiles can be catalyzed by a very cheap catalyst such as a clay, smectite, and so on. So this technology has some advantages, but too expensive. Certainly there would be another group of renewables, and that is starch, cellulose, sugars, and in addition to these all your chemicals, and for synthesis of value-added chemicals. And I don't want to go to discuss that with you now anymore, just to give you a flavor. Who is this? That is my second grandchild, Amelie. She was 3 days old. Now, Mara, what does she need in addition to the mother milk? What do you think? Diapers, sure. So, there was a program with Procter & Gamble, and that is the ad of Procter & Gamble. And that means the bump of the kids means everything. And such diapers can be made out of starch. Yeah? You can make super absorbers. You can make surfactants and so on. Everything out of starch. And I said to you, you can make new materials with favorable properties, surface active properties, and we can convert, for example, starch here with 20%, but we get a nice selectivity of the oxidation in the 6th position here, very nicely, 100%, and out of that we can make polyesters. Yeah. Okay. I mentioned to you already, it's too expensive. We must have a higher oil price, that some of our, and also the oil has to be diminished. After, when that will happen, then it might be worthwhile to use this new technology. But let me finish with that. That's you, me, the researchers of companies. And they develop something new, a new tool, new material. And then the consultants come and say, oh, that's excellent what you developed. And they go with that information to the board and say, your chemists have developed a new technology, fantastic. You should use it. And then they get sorry, there is no time for new technology. I have got a battle to fight, still using the old technology. What do I want to say? We have to compare the costs, the investment of the new technology compared to the already existing paid-off technologies, which we still use. Yeah, with that, thank you very much for your kind attention.
People might need to go, so in that case, but if we have time for questions, we have time for questions if people have them here. Maybe I'll start out and ask, in the last topic on the epoxidation, I noticed that you were using organic hydroperoxide, which is more expensive than the hydrogen peroxide. And would there be an opportunity to decrease the cost of these products, these nice products that you're making, by using a zeolite in conjunction with hydrogen peroxide?
No. If you looked carefully, we used also titanium TS1. But you do not get any conversion.
What
here.
about larger zeolites, like beta or maybe something
Even
else?
in that case.
Even
You need, to avoid any diffusion problems, you need 40 to 60 angstrom diameter. Yeah? So that's not possible. It would be certainly a cost-saving part when we can replace the tetrabutyl hydroperoxide by hydrogen peroxide. Would save a lot of money. But you have to see the properties of these materials. They are all not hydrophobic so much, in contrast to TS1. TS1 is very hydrophobic. So the water is repelled from the surface, and you have always fresh surface. Not in the case of this titanium MCM41. Therefore, you have to use this tetrabutyl hydroperoxide, unfortunately. But it's certainly a topic for investigations. Yeah.
Thanks. Other questions? Maybe from graduate students. This is a graduate student invitation.
It seems that everything was clear, huh?
Yes.
Or it was not so clear, nobody understood anything. So
It's also late. So how about I ask this, if you have questions, please come and see Professor Holderich here after the seminar. He'll be here. And please join me in thanking him one more